announcing. There we go. So we'll have some updates on stuff returned to you for Friday, and I should have most of the exam grading done by Monday. So we'll plan on spending time, a little bit of time Monday in class to go through that and have solutions up for you for that. So the exam is not as bad as you guys think it is. I'm actually pretty pleased, given the difficulty with it, what I've read and looked at so far. Oh man, my hair is totally woofing today. Okay, well anyway, let's jump back into interdiffusion, because this was where we ended on Monday, and I was rushed, and so there are the reason why I don't want to talk about the exam right now is there's still a couple people who have extensions for medical or other reasons, and so we can relax our requirement, right? If you know, I'll take it on the honor system, right? If you guys know that the other person you're talking to has turned theirs in and does not have it open, feel free to discuss amongst yourselves. Yes, clam down. But anyway, it's if venting provides some catharsis, go right ahead. But don't panic. Everyone's doing fine. Okay. Anyway, for this interdiffusion and the Kirkendall effect, I rushed this a little bit at the end of Monday, and I'm afraid I may have said something confusing. So I want to take a couple seconds and go through this a little bit more carefully. So here we have a diffusion couple between A and B, right? We stick them together with some inert markers like the molybdenum fine and molybdenum wire in the experiment from Kirkendall, right? And where they are originally in intimate contact, this is known as the metano plane or the metano interface, right? And after time, there is going to be A is going to move into B and B is going to move into A, but they're going to move at different rates, right? So what we have here is a greater flux of B than of A, right? So that means my markers are going to move, right? If you have an experiment with markers, it's easy to see where they would, how far they move. Where the markers are is called the Kirkendall plane. In an experiment without markers, if you just have a diffusion couple, the position that the markers would end up is still called the Kirkendall plane. So if you're looking into the diffusion literature, and you will sometimes come across the words metano plane and Kirkendall plane, and that's referring to where the interface was initially and where the interface is due to convection of the lattice, right? And so because B is moving more, right, we have a net flow of vacancies going over to this side, right? And because the vacancies can't be destroyed at a fast enough rate, they can form into pores and form sinks over here, right? Right? And the position of the pores is going to be between the metano plane and the Kirkendall plane, right? Okay, so hopefully that part is clear, where I think, oops, what I want is, where I went a little fast is when we were talking about this. I said, where will the voids form? And I pointed out the interdiffusivity, and I think I may have given some people the wrong idea, right? The important thing to look at is look at the relative diffusivities, right? Copper, the self-diffusivity of copper and copper is much higher than the diffusivity of nickel and copper, right? And the diffusivity of copper and nickel is higher than the diffusivity of nickel and nickel, right? So no matter at any concentration, the diffusivity of the diffusivity of the copper is faster than the diffusivity of the nickel, right? So that means if I have a net flux of, if the copper is always moving faster towards the nickel than the nickel is moving back, I'm going to have higher vacancy formation. So the size is not really the only thing that matters, right? It's also the bonding, right? Well, they're metals, right? So we still have metallic bonding, so we don't have ionic charge in the same way, right? But it's the bonding, right? Nickel is much stiffer than copper. It has a higher melting temperature, right? So nickel forms essentially just a stronger atomic bonds than copper, right? Right. Again, we're not necessarily making chemical bonds, right? We have to, I mean, I guess we are, but we're not in terms of I got to be careful, right? Because if I say valence doesn't matter, that's totally not true, right? The best thing to do is really to look at the bond strength, which you can get at from looking at the melting temperature and the elastic modulus values, right? Those are going to be the most important properties in looking at what ranking the diffusions, right? So the higher your melting temperature, the lower your diffusivity is going to be, right? And the melting point of nickel is significantly higher than the melting point of copper, right? So it's part of it, the self-diffusivity. So where these points are going to be related to how tight that bonding is, the depth of the potential well, right? So, okay, so real example, Kirkendall voids are a real thing for interdiffusion, right? Okay, so we have to consider that there are other diffusion paths, right? We talked before, we were talking about bulk diffusion, but we have some short circuit paths, right? And whether or not these carry a significant amount of whether or not these paths end up being significant depends upon the temperature and the amount of them, right? You can have a sort of a meandering wide river that's moving very slowly. And you can have a turbo pump, right, that's sucking material at a very high rate. But if it's only connected to a 1/2-inch tube, right, it doesn't matter how fast the velocity of that turbo pump can, or that pump can move things out of the river, right? It's an insignificant amount of flow relative to this huge, wide, slow-moving body, right? So the diffusivity tells you how fast something can move along a certain path, but it doesn't tell you anything about how much that path actually accommodates, right? So if I have a big sample, right, the amount of atoms on the surface relative to the volume is very small, right? And the same thing if I have large grains, the amount of grain boundary area I have relative to the bulk of my grain is also very small, right? But if we look at a diffusion in polycrystal samples, a lot of times you see that there's a faster diffusion on the grain boundary than there is through the bulk, right? And so atoms, in this case A, if we look very near the grain boundary, A will penetrate much farther along the grain boundary than it will on the in the bulk, right? But again, we have to consider the relative amount of grain boundary volume relative to the bulk, right? So if we say our grain boundary has some kind of effective thickness, right, and we have a grain boundary diameter, we can calculate the volume, the effective volume that transport can happen through along the grain boundary relative to the bulk, right? And we can calculate an apparent diffusivity. That's a combination of bulk diffusion and grain boundary diffusion, right? Both of these are going to have a temperature dependence that's Arrhenius in the same way, right? Right, they're going to have potentially different activation volumes, but they're both going to be, sort of exponential with temperature. But this bulk term has a much higher cross-sectional area, right? Much larger area for flux to go through than the grain boundary term. So if we look here, the notation in on this picture is a little different than what I used before. So here D1 in your reading means bulk. I think that's confusing. And DB is grain boundary. Why they use B for grain boundary and 1 for bulk, I don't know. But anyway, so here's the grain boundary, right? Diffusivity. So it's always at a higher the diffusivity is always higher, right? Here's our bulk. And what we see is that at high temperatures, right, this is the inverse temperature. So as we come close to 0, this becomes higher and higher. As we get at higher temperatures, the apparent diffusivity is very, very close to the bulk. But then as we get to lower temperatures, the effective grain boundary diffusion kicks in, right? And there's actually a deeper message, I think, here than just the relative diffusivities, right? And this is something, a trend that you see over and over again, that in general, the lower the activation energy that something has, the smaller the temperature dependence it's going to have, right? One example of that is where this rule comes in handy is thinking about the temperature dependence of deformation in different crystal structures, right? FCC crystals, right? I've got 12 independent and degenerate slip systems, right? My 111 planes along the 110 type directions, right? My close pack planes and my close pack directions in FCC are my slip systems, right? It's really easy to move dislocations along those directions. Now, if I look at BCC, I don't have close packed planes in BCC. And my slip planes are the 110 type planes, and my slip directions are 111. So just the inverse of FCC. But I have lots of other more difficult to operate slip systems in BCC. But in general, they're all going to have a higher activation energy, which means that I'm going to have a really very large temperature dependence for my yield strength in BCC materials, where I'll have a much smaller temperature dependence in FCC, right? So we can say at room temperature, BCC is going to tend to be stronger, but its yield strength is going to drop much faster with increasing temperature than FCC will. Right, we see the same thing here for diffusion, right? The effective diffusivity, right? The slope for bulk diffusion is going to be much steeper here, which essentially is going to tell us that as we get to higher and higher temperatures, our bulk diffusion is going to be dominant, right? And that our overall diffusivity is not going to be catch up to the grain boundary diffusivity except at very low temperatures, right? So if we extrapolate this out, eventually these two curves will meet, right? And that basically tells us that at very low temperatures, the only diffusion that we're going to have is along grain boundaries or surfaces. That bulk diffusion is effectively going to be completely shut down, right? We also have diffusion along dislocations, right? And this is called pipe diffusion, right? So dislocations can act as important diffusion pathways at low temperatures when our bulk diffusion is virtually impossible, right? But we need a very large number of dislocations, right? Because the pipe, the cross-sectional area of each dislocation is very small. Right. So just another important short circuit path, right? So if you hear the term pipe diffusion, that's what this means. Okay. And then just sort of the last topic that I want to cover on diffusion is diffusion in multi-phase systems, right? So if we look at the concentration, if we're at this temperature, right, what we're going to have is we have alpha, right? And then we enter the two-phase region, right, where we have anywhere we're in between this composition, composition A, and composition B, as our overall bulk, we're going to have alpha at this composition and and B beta at this composition, right? So when we look at our concentration profile, right, what we see is we have gaps in our composition as we go across, right? So we have A, right? Alpha, beta, and gamma are the only regions that are, phases that are going to be in our sample. What we don't see is the two-phase region here, right? So we move from one end of the sample where it start at this composition, we move up in alpha, and then we hit an alpha beta interface where we have pure beta, and there's a composition, a step function in composition from A to B as we cross that interface, right? And we can look at the activity, right, or our chemical potential, and what we see is across our sample, our chemical potential or our activity has to be continuous, right? Remember that chemical potential is the driving force for diffusion, not the composition itself, right? So what we end up with is a profile where we have a continuous activity or chemical potential curve, right? Right? We always have to maintain equilibrium at this interface, right? And these phase boundaries themselves are going to move with diffusion, right? But the exact analysis of this gets really complicated really fast, right? I just want everyone to appreciate that the positions of the alpha beta interface is going to move in the same way that the lattice convex, right? And we can give an expression for the velocity of the interface. But again, I don't want, the purpose of this class isn't quantitative analysis of diffusion. It's just to be able to think about diffusion and diffusivity in the context of the phase transformation, solid state phase transformations and processing that we're going to talk about. Okay, so this weekend I'm going to be posting some reading on diffusion. There'll be a reading quiz, but we're not going to have a dedicated homework assignment on diffusion. Some diffusion related questions will come up on the other homework assignments, right? When we talk about phase transformations and vitrification and crystallization and grain growth and sintering, but we're not going to have a dedicated homework set on diffusion, right? We'll give you guys a little break. So there'll be a phase transformation homework assignment coming up towards the end of next week, and 2 reading assignments that will be posted. Okay, so that wraps up what I wanted to talk about for diffusion, right? Just think about the big main ideas, right? The temperature dependence is going to be is exponential, right? And what we see in terms of Darkin's rules, right? And understanding what's going on with interdiffusion, right? These are just the main sort of big ideas. Get a good physical picture of those in your head and you'll be set for everything, right? And then your time, right? Your distance is always going to be related to the square root of dt. Right? So if you just keep those few simple ideas in your head, you'll be fine with everything you need to do for diffusion, right? Sort of any questions or clarifications before I move on to our start phase transformations? Right? So I don't see anything popping up on the chat. So that means either everyone fell asleep or everyone's just giving a big sigh of relief that there isn't going to be a homework on it and I'm not making you solve all these PDEs. Yeah. No, I mean, in reality, this is something I really hated as a student because there's only like 1 or 2 boundary conditions that you can solve, right? And then anytime you think about a real problem, you can't actually solve it. You need some kind of a numerical thing. When you do mod sim with Professor Brown next semester, there's a module where you have to solve diffusion around a crack tip using finite elements to look at how hydrogen concentrates near stress concentrations and can lead to stress corrosion or hydrogen embrittlement. Right. And I think those are kind of the more useful cases, right? Because to actually have any type of thing, you need to consider the effect of stress and temperature and all of these things. There's only 1 or 2 scenarios like diffusion through a hydrogen storage tank where you can have an analytical solution that actually tells you anything, right? Quantitatively. What I think is really more useful is the types of things you'll see in the homework related to phase transformations where I ask you to think about how diffusion is important to the processing that we actually care about for this class, right? I'll let Jin Woo teach you the deal with the PDEs in transport. So maybe that's laziness on my part, but I think it's better better to get the key ideas I want you to have across than to do complicated math for complicated mathematics' sake. Okay, so this is now really the heart of this class, right? This section on diffusional phase transformations is, I think, like the center topic in material science, right? Because the processing of material to get the microstructure we want that gives us the property and performance we want is the definition of the field of material science. And how do we do it? Most of the time, it means getting the phases that we want where we want them. And for most of those phases, it turns out to be diffusional phase transformations, right? So this is, I really think this is the heart and soul of material science, right? And super critical to the welding engineers, right? you know, I think where would welding engineering be without the optimization of ferritic microstructure, right? I think is you know, we wouldn't be doing too we wouldn't be doing too good in that in the field without a really good understanding of what's happening in terms of phase transformations. Okay, so I want to just start out by talking about a few different types of solid state diffusional transformations, right? So the majority of our phase transformations that occur in the solid state take place by thermally activated atomic movements, right? So most of the time we think about changes in temperature of a material that has a fixed bulk composition, right? So most of processing of metals and a lot of processing of ceramics is let's take something up to the temperature regime to get the phase composition that we want, and then quench it down to room temperature where diffusion is very slow, and we lock our material into a metastable state, right? That's the key thing, right? The key idea behind most of material processing is we're not at the equilibrium microstructure. The equilibrium microstructure for most materials is pretty useless, right? We try and find a metastable structure that gives us the properties we want and lock it into place, right? So we have a couple different types of changes, right? So if we think about pure materials, right? So almost all pure materials, metals, right? Polymers are a special case that we'll deal with sort of separately. Ionic materials, covalent ceramics, glasses, right? All materials really exist in multiple phases at different pressure temperature combinations, right? The most well-known of these is iron to most of you, right? You go from the FCC to BCC transformation in iron, the austenite to ferrite transformation, right? There's also epsilon iron here at higher pressures. That's not shown on this chart. So if this were to go out, there'd be another phase out here, right? Pure water and ice has a myriad of different ice phases, right? Most of these really, though, are of limited engineering interest, right? Very rarely do we ever use pure materials, right? The exception is some ionic materials, but most of the time those are doped, right? We don't typically use high purity ionic, simple ionic stoichiometric ceramics as much as you would think either. Okay, so when we look at these pressure temperature phase diagrams, some of these transitions can be diffusional. Some of them can also be martensitic, right? Graphite to diamond is a martensitic transformation. Most of these ice changes transformations are martensitic because we're at temperatures where diffusional transformations are just too slow, right? But there are diffusional aspects to many of these, right? So that's another sort of subtlety that we'll talk about when we discuss certain types of transformations, is that sometimes we have aspects that are martensitic and diffusional, right? Such as bainite in steels, right? It's not, it's got some thermally activated aspects, and it's got some shear driven aspects, right? The formation of Widmanstätten plates in steels are similar, right? So the line between these are not always as clear cut, right? Okay, so if we look, just for your information, right? Ice has a huge number of crystal structures that are at different temperatures, right? So up here we see some of them, right? But really there's 17 crystal structure, or 17 crystal structures of ice plus amorphous phase. Right, so lots of different phases. Almost all of the ice is actually just our regular hexagonal ice that we get out of our ice makers, right? Virtually all of it is this, but high pressures give us a range, a plethora of other phases. I just think it's really cool. The study of ice and the material science of ice, the deformation behavior of ice, grain growth in ice, recrystallization in ice, is actually a really important topic, which is getting a lot of attention right now because of global warming. It turns out that glaciers and the ice shelves are not behaving in the way that the climate models are predicting really accurately. And a lot of it is because we don't understand the material science of ice nearly as well as we thought we did. So hopefully we'll still have ice in a couple of years. That sea ice will still be a thing. With the way we're going, I'm not so sure about that. But either way, it'll still be important to keep studying it so that eventually we can hope to see its return. Okay, so the first really important engineering solid state phase transformation. Yeah, Ohio's coastal, right? We don't need to worry about our flood insurance here. Right, the first really important engineering reaction phase transformation is precipitation, right? So obviously we know if I take a material and I hold it in this single phase alpha region and I cool it down, I'm going to transform to alpha of this composition and this composition, right? So Ohio is, well, there's lots of floodplains that are not coastal, right? Ohio's a strange place for people who are not from Ohio to move to, right? I've been here for 8 years and I still don't understand Ohio at all. Yeah, it's I've never been anywhere else where here's the story I think that sums up Ohio, right? We moved here, and when we first moved, we needed to get a washer and dryer because we didn't move those. We didn't move those with us, so we went to the Lowe's to buy a dryer, and this was the middle of July, and so we look around and we see all these people wearing Ohio shirts, right? nowhere else where I live do people don't wear Pennsylvania shirts. I never saw people wearing New Mexico shirts in New Mexico or New Jersey shirts in New Jersey. So I asked the salesman, like, what's going on? Why is everyone, is it some kind of holiday? Why is everyone wearing Ohio gear? And the salesperson was like, what are you talking about? That's just the way people dress all the time. So yeah, it's just that I think just sums it all up. And what's weird is Ohio doesn't have a what's the word I'm looking for? A quintessential cuisine, I think, right? There is no dish that says this is Ohio, right? With the exception of Skyline chili, which I think is just really weird, right? So yeah, you have one tiny little candy. Corn, lots of places have corn, right? So I think Skyline and Mr. Hero are the only like actual native Ohio cuisine. Okay, anyway, that's a tangent. People not from Ohio. Oh yeah, Wendy's and White Castle. I forgot about those. Right? But, you know, Ohio doesn't have a cheesesteak, right? It doesn't have New York pizza. Oh, and square cut pizza. Ohio pizza is just gross. I can't.
You've obviously never tried Massey's.
Yeah, I have. I mean, living in New York and New Jersey and Philadelphia for so long, right? You have awesome New York pizza on every corner. Right? Every pizza shop you go into is phenomenal. Right? And you get into it's just weird. The crust is flaky. Oh, right? Jets is actually Detroit style pizza. So, you know, yeah, we don't have, there's no good, you know, bagels. I'm sorry. Yeah, I don't know. It's just, okay, Ohio ice cream. Sarah's got it. We've got a winner. Ohio has the best ice cream. I'll give it that. Everywhere in Ohio has a really great local ice cream shop. Right? Which is probably why I'm fatter than when I moved here. No traffic. Ohio also has the fact that parking is cheap everywhere. Right? That's another bonus that Ohio
except does. On campus.
Except on campus, yes. But Columbus, Cincinnati, Cleveland, cheap parking and not big and not a lot of traffic. Yeah, but still, even parking for events is really cheap compared to lots of other places. Right? Try to go to Boston, right? You're going to look at like $50 to park for a Bruins game. Okay. Well, anyway, diffusional phase transformations, right? Everyone knows if we start at alpha and we cool down at this composition, we're going to decompose into alpha at this composition and beta at this composition, right? So normally, though, in processing, we're not going to slowly cool, right? What we'll do is we'll homogenize and we'll get uniform alpha at this composition, right? and then quench down to some temperature here. So now if I quench down and I rapidly change my temperature, I now have metastable alpha, right? That's going to decompose to this composition and this composition, right? And it's important to realize that we're going to get a very different microstructure if we cool slowly versus if we quench down quickly. Right? The other thing to realize is that we're going to have a composition change everywhere, right? Because the alpha that remains is going to be over here, and we have beta over here. And this precipitation, the growth of beta from this alpha, requires long-range diffusion. It requires moving beta out of the alpha into the, B out of the alpha and into the beta precipitates, right? So because this requires long-range diffusion, we can quench it out. We can get the microstructure we want and quench down and maintain it metastably, right? So precipitation is the first one. Yeah, it's really hard. In Ohio, my wife still is used to driving 20, 25 miles over the speed limit constantly, everywhere, no matter where she goes. Ohio people don't have a hard time with that sometimes. Okay, so the next really important diffusional transformation is eutectoid reaction. So we start up here in the full gamma regime and quench down. So here now we have metastable gamma going to alpha plus beta rather than alpha prime going to alpha plus beta that we would have over here, right? So again, this requires a composition change, requires long-range diffusion, and it's quenchable, right? And it's going to depend on the cooling rate. So we'll see that the rate at which we cool down and the rate at which we quench is going to give us different microstructures, right? The big example of this is austenite going to ferrite plus cementite in steels, right? So the formation of a pearlitic steel, right, is a example of a eutectoid reaction. Okay. We also have ordering, right? So we talked about ordered phases at the beginning when we talked about microstructure things, right? And here we have a high temperature random solution. And as we go down in temperature, we become an ordered phase, right? Now, the important thing to realize about this transformation is it doesn't require long-range diffusion. We still require diffusion because we have to swap atomic positions, but it's only diffusing over short range. We only need our atoms to move over a couple atomic positions. We do not need them to go long range, and there doesn't have to be a local composition change, right? So that's the big distinction, right? Because it doesn't require long range diffusion, it's very difficult to stabilize the random disordered solution at lower temperatures, right? It's going to have a tendency to order even at lower temperatures because we don't require long range diffusion and we don't require a composition change, right? Massive transformations are the same way, right? A massive transformation is the decomposition of a metastable phase. So if we start up here in this beta phase field and we quench down, now we're in the alpha phase field, but both alpha and beta are stable at these compositions at the relevant temperature, right? So that means we're going to be changing the crystal structure, but we don't require a composition change of our material or any long-range diffusion, right? So massive transformations are, again, very difficult to stabilize because we don't require long-range diffusion or composition changes, right? It can go from beta to alpha with very little thermal activation. Okay, so those are the main types of diffusional transformations, right? On Friday, we'll talk about interfaces and interfaces because these interfaces are really important, because when we think about nucleation of secondary phases of phase transformations in the solid, right? This looks an awful lot like what you saw for the solidification for liquid to solid phase transformation, except we have an additional term, right? We have our interface term, which is going to go as R squared. We have an additional term that has to do with the strain energy, right? The coherency strain near those interface and the volumetric strains that come up, right? And that's intimately tied in with the interface, with the interfaces, right? And so understanding solid-solid interfaces is critical to being able to understand the nucleation behavior, right? And that will be the topic for Friday. Okay, we'll stop there. Everyone should have more homework grades posted by Friday, and Monday we'll start talking about the exam. Okay, so take care. No, there is definitely no reading quiz and reading assignment due this Friday. It'll be the diffusion reading will be reading the diffusion reading. The diffusion reading will be posted today, but there'll be a quiz sometime next. The reading quiz will be sometime next week. Okay. Take care, everyone.